In this video, we are continuing our focus on acids and bases, looking at Bronsted-Lowry acids and bases. Now, as we consider Bronsted-Lowry acids and bases, in particular, let's start with acids. How can we compare acid strength? Well, the acid strength is defined by the reaction in water. So let's say we have a generic acid, HA, and this reacts with water. So in this reaction, HA will be our acid and water will be our base. So the base will use a pair of electrons to grab a proton, and these electrons will move back onto the A, giving us A minus, and we have, this still has its lone pair, but now the oxygen is connected to the hydrogen that it took from HA. So what's left after the acid has acted as an acid is A minus. What's formed when water acts as a base and grabs a proton is H3O, and I forgot plus, because the oxygen now has a formal charge of +1. If we were to think about this reaction happening in the opposite direction, because this is a reaction at equilibrium. So that means that the reaction can happen in the forward direction and it can happen in the reverse direction. You talked about equilibrium reactions in general chemistry, and keep in mind what that means is just that the reaction happens in the forward direction and the reaction happens in the reverse direction. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, which means even though both reactions are happening, the concentration of all of the species are going to remain constant. Because we have the forward reaction and the reverse reaction, let's identify our species in the reverse reaction. In the reverse reaction, this would act as the base, grabbing off a proton to form HA and water. And so we call this our conjugate acid, and this is our conjugate base. So whatever results from the acid is the conjugate base. It's the base because in the reverse direction, this would act as the base and grab off a proton. Whatever results from the base is the conjugate acid. It's the acid because in the reverse direction, this is what loses a proton to form this. Now for any equilibrium reaction, once the reaction has reached equilibrium so that the concentration of reactants and products are no longer changing, even though the forward and reverse reactions are still happening, we can write an equilibrium expression. And so we have the equilibrium constant, which is represented by a capital K. This is equal to the concentration of products divided by the concentration of reactants. So for any equilibrium, we can write an equilibrium expression that says the equilibrium constant, capital K, is equal to the concentration of products over the concentration of reactants. You're going to see many examples where we will specify the terms, where there are exponents, but we're going to keep this relatively simple for now because we're only talking about acid-base reactions. So rather than talking about a general equilibrium constant K, we can specify the acid dissociation constant Ka. So Ka is defined when we have an HA reacting with water. And we can think of this as this HA is dissociating to form H3O plus with water and A minus. So our equilibrium constant Ka is given by the concentration of products, which in this case would be A minus times the concentration of H3O plus divided by the concentration of reactants. So our reactants are HA times water. But in this type of reaction, water would be our solvent. And so the concentration of solvent is so much bigger than the concentration of other reactants or products that over the course of the reaction, the concentration of water essentially doesn't change. So this is constant, therefore it's taken into consideration within the equilibrium constant. So we do not include the concentration of the solvent because that would be incorporated into the Ka, into the equilibrium constant. So that means that what we have for the Ka is concentration of A minus times the concentration of H3O plus divided by the concentration of HA. So this is the term for the acid dissociation. Now, if we were to consider a strong acid, for this, HA plus water, the equilibrium lies very, very far to the right to give H3O plus and A minus. Now, with the equilibrium lying very far to the right, that means once this reaction has established equilibrium, we're going to have lots of products and very little starting material. So our Ka, which is equal to H3O plus times A minus divided by HA, because these concentrations will be really large and this concentration will be really small. Overall, that means our numerator is very large and our denominator is very small, and so this is going to be a big number. On the other hand, if we have a weak acid is one that does not dissociate much in water. So HA plus water, our equilibrium lies toward the reactants. Ka is equal to H3O plus times A minus divided by the concentration of HA. But because the equilibrium lies to the left, that means we're going to have a very small concentration of H3O plus and A minus, and so the numerator will be small. We will have a very large concentration of HA, which means the denominator will be large. So overall, the Ka is going to be small. So kind of as a first estimate, we can think about a Ka that is big is going to be greater than 1. A Ka that is small is going to be less than 1. So let's continue to think about the acid dissociation constant. And once again, we are considering the concentration of H3O plus times the concentration of A minus divided by the concentration of HA. Because for any equilibrium constant, we have the concentration of products divided by the concentration of reactants, but we do not include the concentration of the solvent because that's incorporated into the equilibrium constant. So the nice thing about the Ka is that it has a physical meaning regarding the position of equilibrium. If we have a Ka that is greater than 1, we know that that means that there's more of our products than reactants. And so we can tell that the equilibrium lies to the right. If our Ka is less than 1, then that means our denominator must be bigger than our numerator, which means we have more of our starting material than we do of our products. So Ka is useful because it has this physical meaning. And if we have, a Ka of 10 or 0.1, then it's really easy to have meaning of that. But the values of Ka can be much, much, much bigger or much, much, much smaller. So for example, it's possible to have a Ka that is equal to 1 million. All right, so we know that's a strong acid. Great. And for another acid, we could have a Ka that is 0.0000001, for example. And we know that that's a weak acid. But although it has physical meaning, let's face it, it's kind of hard to work with really large and really small numbers. Yes, we can use scientific notation, but it's still not the most convenient way to be able to compare the strength of different acids, or to be able to consider what we have present in solution. So rather than dealing with really large numbers and really small numbers and having to use scientific notation and exponents, instead, chemists rely on the pKa. Now, the pKa is equal to the negative of the log of the Ka. Now, the pKa, you also may have heard of pH. Really, the p anything is equal to the negative of the log of anything, okay, whatever that represents. So for the pKa, this is the negative of the log of the Ka. Unfortunately, this takes away from the meaning of the Ka, where here we have this direct comparison of the numerator and the denominator. But once we do have the pKa, it is a lot easier to use. Now, I encourage you to take a few values. So take a value of 1,000,000 and plug it into your calculator, take the log, take the negative of that to calculate the pKa. This might not work on your phone. You have to make sure that you have the ability to take the log. So if, for example, we look at 1,000,000, I am right now plugging into my phone 1,000,000. If I take the log of that, that gives me 6. And then if I take the negative of that, that gives me a -6. Now I am plugging in, I have 6 zeros after the decimal point. If I take the log of that, that gives me a -7. And then the negative of -7 is 7. So what we see then is that a large value for Ka gives us a small value for pKa. A small value for Ka gives us a large value for the pKa. So our range could be on the order of -6, -7, -8, all the way up to about 60. So it's still a nice big range, but we're still not dealing with exponents. So it's important to keep in mind that a strong acid has a large Ka, but a small pKa. And a weak acid has a small Ka, but a large pKa. So once again, if we can think about the scale, a large Ka might be up to 10 to the 7th power, for example, and a Ka could be on the order of 10 to the -7, right? So this is a huge range of values. But when it comes to pKa, some of the strongest acids that I can think of offhand would have a pKa of about -8, and some of the weakest acids have a pKa of about 60. So it gives you a very broad range, but not as huge as what we have for Ka. So when it comes to comparing the strength of acids, we want to consider the pKa, which is defined from the Ka, the equilibrium constant, defined from the acid dissociation in water. Once we have the pKa values, now we can look at a pair of acids and decide which one is the stronger acid, which one is the weaker acid. Now here we have a few tables of pKa values. The first one is within your textbook, table 2.3, and then the second one is also from your textbook, but this is in Appendix B. So in this table, we have our acid, and then the name and the pKa, and then it shows the conjugate base. So once this acid has acted as an acid, given up a proton, then what we have left is the conjugate base, which is called ethoxide. Water has a pKa of about 15.7. Its conjugate base is hydroxide. So looking at pKa's, we're going from 16, 15.7, down to 2, down to -1, -7. So here we are going stronger acids, And then our stronger acid has a conjugate base that is weaker. Our weaker acid has a conjugate base that is stronger. So increasing acid strength means a smaller pKa value. Increasing base strength would be the conjugate base of weaker acids. Looking at Appendix B, this one, it just shows the acid itself and the pKa. In addition to these tables, there are tons of tables of pKa values that have different representations. It will include different compounds, and in some cases, it'll also include pKa values in water compared to other solvents as well. Now, in Gen Chem or high school chemistry, you might have talked about a few particular acids, such as nitric acid, HNO3. This has a pKa of negative 1.3. Hydrochloric acid, HCl, negative 7. But we need to focus on some other types of acids as well. From slide 4, we had a few examples of organic acids and bases. Ethanol was one of them, and that has a pKa of about 16. Another alcohol is methanol, and this has a pKa of about 15. Another example that we looked at on slide 4 is acetic acid. Acetic acid is here on this table, and this has a pKa of 4.7. Also on our notes, we had acetone, which is here in this table. That has a pKa of about 19. We had propane, and so propane is not directly on this table, but similar to it, we have what's called methane, and this has a pKa of about 60. So really, really weak acid with a really high pKa. Also on slide 4, we had a compound with a carbon-carbon double bond, an alkene. So here's an example, and that has a pKa of 44. And we had a carbon-carbon triple bond, and here we're looking at a pKa of about 25, 26. So again, in terms of some of the strong acids that you might have talked about in general chemistry or in your high school chemistry class, for example, we have things like nitric acid, hydrochloric acid, sulfuric acid, H2SO4, that has a pKa of about negative 5. But in terms of organic acids, we have something like acetic acid, which is 4.7. Water has a pKa of 15.7. Alcohols have a pKa of about 15, 16, something like that. And then an alkane, now we're going to the extreme in terms of weak acid, this has a pKa of about 60. In some cases, you will have access to tables of pKa values, and then you just have to be careful that you're reading the table the correct way to get the correct pKa value. In other cases, you might not have the exact same compound available in a pKa table, but you'll come to understand what would be a reasonable approximation so that you can look at a compound on the table that is similar enough to your compound that you can use it to estimate the pKa. So we've spent all this time talking about how to compare acid strength, and we'll focus on pKa. The smaller the pKa, the stronger the acid. The larger the pKa, the weaker the acid. What about base strength? Well, it's possible to consider a base such as NH3 reacting with water to give ammonium ion plus OH minus, and we can write the equilibrium expression for this as the Kb, the base dissociation constant, and we could determine tables of pKb values. But that means a lot more data that has to be collected, a lot more data that has to be compiled into tables, and we don't need pKb values, right? We don't need to use the Kb or the pKb because we can compare base strength using pKa's. So let's just stick with pKa's. So for example, let's say we are looking at hydrochloric acid reacting with ammonia to form ammonium ion plus chloride. So Ammonia is acting as the base. It grabs off a proton from HCl. With its extra proton, it's now NH4, and there's a positive formal charge on the nitrogen. Without the H plus, that pair of electrons that used to be shared between the hydrogen and the chlorine are now on the chlorine as another lone pair, which gives chlorine a negative formal charge. So in this reaction, HCl is the acid and ammonia is the base. Then after ammonia acted as the base, it becomes the conjugate acid. After HCl has acted as the acid, what's left is the conjugate base. Double check your definition of conjugate acid and conjugate base, because in the reverse direction, this means that this acts as the base, grabs off the proton from the acid to give these two products. So yes, that looks good. In the forward direction, this is acid, this is base. In the reverse direction, this is acid, this is base. Once we have identified our acids, we need to use the pKa values of the acids. So for HCl, depending on what table we're using, HCl has a pKa of negative 3.9. Let me just specify these are the pKa values. And then ammonium ion has a pKa of 9.4. So when we are comparing pKa values, we know that the smaller pKa is the stronger acid. So that means this is the stronger acid and this is the weaker acid. Furthermore, we know that the conjugate of the stronger acid is going to be the weaker base. The conjugate base of the weaker acid is going to be the stronger base. So by comparing the relative strength of acids, we can also compare the relative strength of their conjugate bases. And so our stronger acid has the weaker conjugate base. Our weaker acid has the stronger conjugate base, which means we were now able to compare that ammonia is the stronger base and chloride is the weaker base. So we don't have to have tables of pKb values. We can use the pKa values. Let's look at another example, and let's say we don't have it set up in an equation, but we're just trying to figure out which one of these would be the stronger base. So this one is called pyridine, and we want to compare it to ammonia. So we want to figure out which one is the stronger base. Well, we cannot compare pyridine and ammonia directly. We need to compare their conjugate acids. So the conjugate acid of pyridine is called pyridinium. So if nitrogen grabbed a proton, we still have these double bonds. Nitrogen now has a formal charge of +1 on the nitrogen. And you can find this in a table of pKa values. So the pKa of pyridinium ion is 5.2. Now for ammonia, NH3, the conjugate acid is NH4 plus the ammonium ion, and this pKa is 9.3. So comparing our pKa values, 5.2 compared to 9.3, this is the smaller pKa, which means this is the stronger acid, therefore this one is the weaker acid. But the stronger acid has the weaker conjugate base, and the weaker acid has the stronger conjugate base. So by using the pKa values of the conjugate acids, we can determine which one is the stronger base. So ammonia is a stronger base than pyridine. Please keep in mind as I talk about SA, SB, WA, WB, I am saying stronger acid, stronger base, weaker acid, weaker base. In some cases, we can categorize certain things as strong acids, strong bases, and certain things as weak acids, weak bases. But in general, Whether something is strong or weak completely depends on what we're reacting it with. And so trying to have some absolute definition of strong or weak is not really that useful because we want to make comparisons within a particular situation. So we could have an example where ammonia is the strong base, but we could also have another system set up where ammonia is weaker than another base that's present. And so mainly what we want to focus on is the stronger acid in a particular reaction, the weaker acid in a particular reaction. And so stronger versus weaker, it's all relative.